Okay, good morning. So, in previous class, we have obtained the derivation or the flexural formula we have derived. In this flexural formula, you have the relationship between bending moment, the stress in the beam, and the radius of curvature. Okay, so it is relating these three ratios over here: m by I is equal to E by R is equal to sigma B by Y. Okay, bending stress. Sigma B is the bending stress. So this was the relationship what we obtained, and further we came across few terminologies, definitions. That is, one was modulus of rupture, and this modulus of rupture is the maximum bending stress in the beam during the failure, just before the beam is about to fail. Okay, so what is the stress in that beam? What is the maximum stress that is developed in the beam? That is the modulus of rupture here. Okay, so knowing this modulus of rupture of any beam, you can limit the stress within that beam. You can limit the bending moment on that beam and see that it is safe, it will not fail. So the next one is the section modulus. Section modulus is a geometrical property over here. So it is obtained by taking the ratio of moment of inertia and the distance of extreme fiber. Okay. So Z, Y is now extreme fiber. It will be taken as extreme fiber distance. So Z is equal to I by Y max. Moment of inertia divided by the distance of extreme fiber measured from the neutral axis. Measured from the neutral axis. So normally it is represented by this letter Z. Okay, so Z will be the section modulus, which is equal to I by Y max. Now after that, another term was the flexural rigidity. Okay, so this product EI, it is called the flexural rigidity of the section or of the beam. Okay, so that is the flexural rigidity. The product EI, product of modulus of elasticity and the moment of inertia. This product is known as flexural rigidity. After this, one more is the moment of resistance. So this moment of resistance is the maximum bending moment that the beam can withstand without failing. Okay, so how do I find this maximum moment? So if I know what stresses are permitted in the material, okay, and by the cross section I can calculate I and Y. Okay, so Y we have to choose for the beam, either it may be extreme distance of the fiber from the neutral axis. So I can now obtain what is the moment that can the beam can take up, or the section, actually the cross section can withstand. So the maximum moment which the cross section can withstand based on this permissible stress and its cross sectional properties. Okay, so I depends on the cross section of the uh, member. So based on that values I can decide what maximum moment the beam can resist. Okay, so this is called the moment of resistance. So how do I obtain this moment of resistance? I'll take this flexural formula, m by I is equal to sigma by Y. These two ratios I'll consider. Now I can express m as sigma by I into Y, or in other terms, this I by Y is nothing but Z, section modulus. So this moment of resistance can also be written as sigma into Z. Okay, permissible bending stress in the beam into the section modulus, that will be nothing but the moment of resistance. So by definition, this is the maximum bending moment that the beam can withstand without failure. Okay, all right, we'll look into the section modulus. So we can arrive at section modulus by knowing the cross sectional dimensions of the beam. Okay, so here say for example, if you have a rectangular cross section, let us say we have a rectangular cross section for our beam, then in that case the section modulus, okay, section modulus, it is normal, it is expressed as so Z will be equal to I by Y max. Okay, distance of extreme fiber from the neutral axis. Okay, so here for the rectangular section, I will be b d cube by 12. Okay, b d cube by 12. So that is the moment of inertia of the rectangular section about its centroidal axis. Now, what is Ymax here? Distance of extreme fiber measured from the neutral axis. So my neutral axis is coinciding with the centroidal axis. It will be exactly at the center over here, center of this depth. This is the depth of the beam, okay, and width of beam is b. So this is what we have over here. So what is the distance of extreme fiber? Ymax. So in this case, Ymax will be d by 2. Neutral axis and centroidal axis are coinciding. So centroidal axis, in case of a rectangular section, it will be exactly at d by 2 here. So the farthest point on this beam for me is at a distance of d by 2 from the neutral axis. So Ymax will be equal to d by 2. Therefore, what we have, Z will be equal to b dq by 12 divided by d by 2. So that gives us as section modulus as b d square by 6. So this is the section modulus for a rectangular section. Okay. So in case of rectangular section, the section modulus comes out to be bd square by 6. I took the moment of inertia of this rectangular section, which is bdq by 12. I divided that by Ymax, distance of extreme fiber from the neutral axis. So here in this case, it will be neutral axis is here exactly at the middle depth of the beam. So Ymax extreme fiber distance is from here to here, this one, or you may take bottom also, either top or bottom, both are same in this case. Okay, if it is a symmetric section, both will be same. So d by 2 is Ymax. So I by Ymax, bdq by 12 by d by 2. It comes out as bd square by 6. Okay. Similarly, in case of a circular section, what I have, the moment of inertia for a circular section, so that will be pi by 64, pi d raised to 4 upon 64. So that will be pi by 64 into d raised to 4. Okay. And Ymax, what is Ymax now in this case? Here also, the neutral axis and centroidal axis are coinciding. We have concluded that in one of our derivation. So what is this Ymax now from the neutral axis? If I measure the distance of extreme fiber from the neutral axis, since it is also symmetric section, you can take on both sides, you'll get Ymax to be same on top as well as on bottom. So Ymax will be equal to half the diameter, d by 2. Okay. So what will be Z here? Section modulus in our case. So that will be Z will be equal to I by Ymax, which is pi by 64 into d raised to 4 divided by d by 2. Okay. Or Z comes out to be pi d cube upon 32 over here for a circular section. So this is the section modulus for a circular section here. Similarly, we can have for other section also. If you have some T section or I section, we have to actually calculate what is its this one I value, then determine the distance of extreme fiber from the neutral axis or from the centroidal axis, then we can do it. Okay, for that we need to do the calculation. But there are some regular shapes for which we can know or remember these values. Another such shape will be a hollow rectangle section. Okay, say for you have a hollow rectangle section. This is a these are all sections what we come in our construction. We'll be having such sections every now and then. Okay, so that is my hollow rectangle section like this. So let us say this is of dimensions. The width is b over here, depth is d. Okay, overall depth. Okay, and then in that case, let me take the thickness. Okay, so I'll call this as d, capital D, and this as capital B. The outer dimensions are capital D and B, whereas if you take these inner dimensions, okay, so this is b, so small d. Okay, depth of this inner rectangle, and this is b. So in this case, the I value, it will be b dq by 12 minus b dq by 12. Moment of inertia of that outer rectangle minus the moment of inertia of the inner rectangle, because that is being removed from this total area. So I have to deduct that. So this will be the moment of inertia, or this is b dq by this b dq minus this divided by 12. So that will be the moment of inertia. So in this case also what we have, the centroidal axis is exactly at the center, okay, at a distance of d by 2. Okay, so this is the distance of extreme edge of the section from the neutral axis. Centroidal axis and neutral axis are coinciding for, say, a straight beam that we are seeing. Then what is the extreme fiber distance? It is capital D by 2, or I will be equal to BDQ by 12, and this BDQ by 12, okay, into this is 1 upon, I can say d by 2 y max. Okay, so this is the how you determine the section modulus for any given cross section. So that is a property what will be required in our problems. Okay, I hope you understood the procedure for determining the section modulus over here. And what we have is next. Okay, so let's take a problem. Right, let us see in this what problem has been given for us. So you can see, list the assumptions made in the theory of simple bending. This is a question paper. What we have. Is the screen visible? What I am sharing now. So this is from December 2017, January 2018 question paper here. So these are previous modules. So in the present module, the first question what has been asked, module number 4. List the assumptions uh, in theory of simple bending. Define section modulus, define modulus of rupture, and moment of resistance. Okay, such questions you'll come across. Now this is a problem. I'll come to that one. Further in this, derive the equation of pure bending. M by I is equal to sigma by Y is equal to E by R with usual notations. Okay, and also one more time, derive the bending equation. M by I is equal to F by Y is equal to E by R with usual notations. Okay, and explain pure bending with a suitable example and mention assumptions of pure bending. Okay, right, we'll come to that problem. I have still not started with the problem, but these are some uh, questions what you come across. Okay, All right. So now coming to the problems on these bending stresses. So first one, let us begin with one simple problem here. A 1 meter long cantilever beam, we can write on that one, a 1 meter long cantilever beam with a rectangular cross section of 75 mm width, 75 mm depth, and 38 mm width of 75 mm depth and 38 mm width is subjected to a bending moment of 2 kilonewton meter at its free end. At its free end, determine determine maximum bending stress be radius uh, of the curvature or the radius of the arc and curvature of the beam. Radius of the arc and the curvature of the beam. Take Young's modulus E is equal to 200 GPa. Okay, so this is the problem what we have, and in this case you have the beam so we have the cantilever beam. This is the problem what is given here. So this is the beam, and extend the moment applied at the free end 2 kilonewton meter, and this is of span 1 meters. Okay, so the cross section is told to us it is of rectangular cross section, and what you have, the dimensions of the cross section are, this is 38 mm and this is 75 mm depth. Okay, so here for this beam we have to find out the maximum bending stress and the radius of the arc as well as the radius of curvature. Okay, so what we have first is we'll find out what is its moment of inertia. Okay, or Let me write what data is given here. Given data is, we have m, okay, bending moment which is equal to 2 kilonewton meter here, okay, and the width of the beam 38 mm, depth of the beam is 75 mm, okay, and span is of 1 meter, and what we have is Young's modulus is given to us. With this, the first thing is moment of inertia, mi, okay, I is equal to bdq by 12 in for a rectangle section. So here in this it is 38 into 75 cube upon 12 here. So what is this value? 38 into 75 cube by 12. This is the value of moment of inertia for the rectangular section. Tell me how much it comes out. Yes, calculate and give me the value of this I. Yes, what is this calculation? You need to have the calculator. I'm not going to do calculation here. You need to tell me the answers. Tell me once you get the answers. Just simple division and multiplication. What is the answer for that?
So 1.3 into 10 raised to 6 meter square.
1.3 into, so how much is that?
10 raised to 6.
This is 1.3 into 10 raised to 6 mm raised to 4. Okay, so this is the I value. Now, what about the distance of extreme fiber? For this rectangle section, what we have seen is this y max. Okay, I want the maximum bending stress, so I'll be considering the distance of extreme fiber from my neutral axis. This is the position of neutral axis, exactly at the center of the depth. Okay, so y max will be equal to d by 2 in case of rectangle section. So this will be 75 by 2, which is 37 point, how much? 5 or 25? 37.5 mm, 37.5 mm. Okay, now due to this bending moment, this will be same throughout the length of the beam. Okay, it is not going to change anywhere around this, anywhere at any point on the beam along this length. Okay, so you take section anywhere over here on this 1 meter length, the bending moment will be 2 kilonewton meter only. So due to this bending stress, these points, okay, on the top and bottom of the beam, they will be experiencing maximum bending stress here. Any point on the top or bottom of the beam along these two edges, they will be experiencing maximum bending stress, because what you have is so in this case Okay. So that is one. So I hope you have written that all this one. So what you have is the bending stress sigma is given by m by I into y. Okay. From where I have taken this, the flexural equation m by is equal to sigma by y. From this relation, I have taken this bending stress formula. Maximum bending stress. Okay. We are asked to find maximum bending stress here. So this is nothing but m by I, maximum bending moment, into y max. Okay. So what you need to consider is the point of maximum bending moment and the distance of extreme fiber at the section. Now here the bending moment is remaining constant. Okay, it is not changing. So this itself is the maximum bending moment, 2 kilonewton meter. So from that what we get is here, if I substitute for that, 2 into 10 raised to 6 Newton mm. Okay, we are working with mm here. So this was 1.3 into 10 raised to 6 mm raised to 4 into 37.5. This is mm, 37.5 mm. So this will be your maximum bending stress. So how much is that? Sigma b value. How much is the value of maximum bending stress?
57.69 newtons.
57.69 Newton per mm square. This is the maximum bending stress. Okay. So once we have this maximum bending stress, the next thing what we'll do is we'll calculate the radius of the arc and also the radius of the curvature. So first is the radius. So once the beam is bent, it will be in the form of arc. So the radius of the arc can be obtained again by taking this flexural formula. Okay, so in this time we'll take the relation m by I is equal to E by R, or R is equal to how much? Okay, so it will be E upon m into I. Okay, that will give me what is the R value. So this is 200 GPa, that is 200 into 10 raised to 3 Newton per mm square, divided by 2 into 10 raised to 6 Newton mm into 1.3 into 10 raised to 6 mm raised to 4. Okay, so this is our radius of the arc. Okay, radius of curvature. So that is nothing but 1 by r over here. Whatever you get, if you take inverse of that 1 by r, that itself will give you radius of curvature. What is the radius of the arc and radius of curvature? What will be this calculation?
So radius is 1.3 into 10 raised to 5 mm.
Okay, 1.3 into 10 raised to 5 mm is the radius. Okay, so radius of curvature will be 1 by r. So if you take this inverse, that will give you what is the radius of curvature.
7.69 into 10 raised to minus 6.
Minus 6. So this will be the radius of curvature. Okay, so this is how we use that flexural formula in our problems. Okay, we'll come to the next problem. What we have. Yes, you can write on this one. A 4-meter long, a 4-meter long wooden beam a 4-meter long wooden beam has a rectangular cross section has a rectangular cross section of 200 mm by 100 mm. Of 200 mm by 100 mm. The beam is simply supported at its ends and is subjected to a point load of 6 kilonewtons at the midspan. Calculate the maximum bending stress calculate the maximum bending stress induced in the beam calculate the maximum bending stress induced in the beam when it is placed on support such that D is equal to 200 mm and B is equal to 100 mm. Second one, D is equal to 100 mm and B is equal to 200 mm. Okay, so that is the two cases what we have. Now the beam is a simply supported beam with the concentrated load applied at the midspan. Here we have that simply supported beam. Okay, so this is the simply supported beam in our case, and at the midspan, what we have is the concentrated load. Okay, so this is the concentrated load applied at the midspan, and it is of 6 kilonewtons. Sorry, 6 kilonewton. This is 4-meter span, and this distance is 2 meter, and this is also 2 meters. Okay, so this is the beam what is given to us. Okay, so what is the maximum bending moment now? When we start with the solution, what we'll have to find is, to know the maximum bending stress, first is we need to have the maximum bending moment. At that point, we'll calculate the bending stress. Okay, so where the bending moment is maximum? In this case, we have come across one of such standard case. The bending moment is maximum at the midspan. Okay, maximum bending moment occurs at midspan when the load is applied at the midspan here, like this. Okay, one of such uh, general case we have solved. Okay, and this bending moment or the maximum bending moment value, it will be equal to WL by 4. We got this formula. If you look into our previous module, we have derived this formula. When a concentrated load is applied at the midspan, what is the maximum bending moment? So that was WL by 4 here. So in this case, maximum bending moment which is WL by 4 will be equal to 6 into 4 divided by 4. So this maximum bending moment will be 6 kilo Newton meter here. Okay, so one is I got this maximum bending moment. So this will be the maximum bending moment and the bending moment diagram here. Okay, so this is how the bending moment diagram will be for this case. Okay, so bending moment is maximum at the under the load. So that is the bending moment diagram. Now with this maximum bending moment, we'll go for determining the bending stress. But there are two cases what is given to us. One, when depth of beam is 200 mm and width is 100 mm. Okay, in two positions we can place that beam. This is a wooden beam of rectangular cross section. What he's telling is, so when the beam is placed on the supports such that its depth is 200, okay, and width is how much? Width is 100 mm. Okay, so this cross section is positioned in this way. So here this is 100, okay, and this is 200 mm. So what I is given is D is equal to 200 mm first case, and B is equal to 100 mm. This is how I am going to place that beam on the supports. Okay, so in this case I will be equal to this BDQ by 12. Okay, so this will be 100 into 200 cube upon 12 here. Okay, this is what our I value will be equal to. What about Y max? Y max will be equal to D by 2. For a rectangular section, it is D by 2, which is 200 by 2, or Y max comes out to be 100 mm. What will be this I value? much this comes out to be? I
66.6 into 10 raised to 6 mm raised to 4.
okay, 66.6 maybe 67 into 10 raised to 4 mm raised to 4 divided by 100. Okay, so you are supposed to actually find I, Y and then Z. Okay, not directly Z. It is better you always go for detailed calculation. It is expected that you do these detailed calculation. So if that is the I value, what will be my section modulus Z, which is I by Y? So 66.67 into 10 raised to how much? 2?
Sir, I value is 66.67 into 10 raised to 6.
10 raised to 6. Okay, 10 raised to 6 means this will be 10 raised to 6, 10 raised to 6. I think this will come out to be 10 raised to 4 mm cube, right? Now, what is the bending stress then? So, bending stress sigma, okay, it will be equal to m by z or even m by I into y. You can use any formula over here, this or this. So 6 kilonewton meter was our maximum unit. That when you convert it to Newton mm, it will be 6 into 10 raised to 6 Newton mm divided by 66.67 into 10 raised to 4. So this sigma will come out to be, in first case, how much it will be? Bending stress
9, sir.
9 Newton per mm square. This is 9.0 Newton per mm square. Okay, so this is what it is in first case. When we go to the second case, others I don't know whether you are calculating or no, it is left to you. So what you have is, in second case, the cross section is placed in this way. Okay, so here in this, what you have is the width of the beam will become 200 mm. Okay, and the depth will become 100 mm. So in second case, what we have is D is equal to 100 mm and P is equal to 200 mm. Okay, so in this case, the moment of inertia will change, the value of moment of inertia. Formula is same, BdQ by 12. So what we have is 200 into 100 cube divided by 12 here. So this will be I. And distance of extreme fiber Y max. So neutral axis, this is the neutral axis. Okay, Y max will be given by d by 2 itself, which is in this case 100 by 2. Y max is 50 mm for us now. What about the I value?
16.6 into 10 raised to 6 mm raised to 4.
60, 60 or
1
16?
6.
1
1
6.
6.
16, sir.
16.6 into 10 raised to 4, correct?
6 6.
6, sir.
10 raised to 6. 16.6 into 10 raised to 6 mm raised to 4. For us now, the section modulus will be I by Y max. So that will be 16.6 into 10 raised to 6 divided by 50. So this Z will be how much? And Yes. How much is that? Section modulus. What will be the Z value?
So 3.3 into 10 raised to 5 mm cube.
Okay, 3.3 into 10 raised to 5 mm raised to 3. Okay, so this will be divided by 3.3 into 10 raised to 5. So sigma maximum bending stress will be now. It will be having the same minimum because load is same, span is same, WL by 4. M will not change, it will be 6 into 10 raised to 6 only. Only thing is section modulus has changed now. What sigma comes out?
So 18.2.
18.
Yes, sir.
Yes, sir.
Okay, 18.2 Newton per mm square. So see, this is the maximum stress what is there. Earlier, what was there? Maximum stress. So here it is 9 Newton per mm square. Okay. So when you reduce the depth, the stresses in the beam is increasing. When the depth is 200 Newton per mm, 200 mm, for the same bending moment value, when depth is 200 mm, maximum stresses were 9 Newton per mm square. Okay. Same cross section, same beam. Only thing is the cross section is rotated now. Now depth is 100 mm here. Okay. So what is happening to the stresses? Stresses are increasing for the same beam, same load. Okay. It is almost doubling, more than double, 18 Newton per mm square. So it is always preferred to have larger depth than the width. Okay, well, let me just come back with that one. So we have 9 Newton per mm square stress here in first case when depth is 200 mm, and when depth is 100 mm, the stresses increase to 18 Newton per mm square, 18.2 Newton per mm square. So increasing the depth of the beam will reduce the stresses in the beam, maximum stresses in the beam. Okay, so it is always preferred to have larger depth. Instead of increasing the width, we always try to go for increased depth of the beam. So if you look at the buildings around you, you'll find that the depth of the beam are always larger compared to its width. Okay, so that is the uh, that will reduce the stresses and it will allow the more load to be carried by the beam. Okay, so that is what we have seen in this particular example in two cases, when depth is 200 mm, when depth is 100 mm. Okay, so depth has more effect on the stresses. Okay, more the depth, lesser will be the stresses in the beam due to bending. Lesser the depth, the stresses will be increased, maximum stresses will get increased over there. Okay, so we'll stop over here, we'll end. You can leave your USN in the chat box.